Hello and welcome to our lecture on transformation of state space models into canonical forms in the subject state space approach to control system analysis and design. In one of the last lectures, we have seen that when we convert these transfer functions to state space models, we can get the state space model into different canonical forms like the diagonal form, the Jordan form, and the first companion form, second companion form. Similarly, a state space representation through an appropriately selected similarity transformation can be converted into companion forms like the diagonal form, the Jordan form, and the companion form. In this lecture, we are going to discuss how we can obtain the transformation to transform the given system into diagonal form, Jordan form, and first companion form. Essentially, it is to obtain the transformation. And of course, there will be examples for each one of them. So first we come to how to transform the state equation into diagonal form. We are given with the state equation x dot equal to ax plus bu, where the matrix A, the system matrix, is in no particular convenient form. And we want to transform it to a diagonal matrix, means to a new basis, new state vector Z, where the system matrix is lambda and we want it to be in diagonal form. And the corresponding input matrix will be beta, of course. This can be done only when the eigenvalues of the matrix A are distinct. So we assume that the eigenvalues of the system matrix A in the given representation are distinct. With that, we proceed, and the procedure goes like this. We obtain the eigenvectors, all the eigenvectors corresponding to the eigenvalues, all the eigenvalues, and we collect them into a matrix V. So V1 is a column, the eigenvector corresponding to lambda 1. V2 is the eigenvector corresponding to the eigenvalue lambda 2, and so on. Vn is the eigenvector corresponding to eigenvalue lambda n. As I told in the beginning that the eigenvalues are distinct, so we have as many eigenvalues, so many eigenvectors. And because the order of the system is n, we have exactly n eigenvalues and eigenvectors. So we assemble them as columns in the matrix V to obtain the matrix V. And this matrix itself is the required transformation which will diagonalize this system to obtain this diagonal system. So the diagonalized system will be lambda equal to V inverse AB, because we saw in the previous video that the transformed system is T inverse AT, that is the system matrix, and T inverse B is the input matrix. So here, because T is denoted as V, the transformation matrix is V, we have V inverse AB will give the new system matrix, and V inverse B will give the new input matrix. We consider one example. Let x dot equal to ax plus bu have this A matrix as the system matrix and this input matrix. So what we do is, we can see, in fact by inspection, you can see this matrix is in triangular form, so it can be easily seen that this system has the eigenvalues -1, -2, and -3. We set up this eigenvalue equation A alpha equal to lambda alpha, where alpha not equal to 0 is to be obtained for each of the eigenvalues lambda 1, lambda 2 and lambda 3. So A alpha equal to lambda alpha, this leads to these three equations for this given A matrix. You can verify that this 1 into alpha 1, minus 1 into alpha 1, minus alpha 1, 1 into alpha 2, 1 into alpha 3, A alpha, first row into alpha 1, alpha 2, alpha 3 column gives this one, equal to lambda alpha gives lambda alpha 1. Second row into alpha 1, alpha 2, alpha 3 will give this one, and right hand side will be lambda alpha 2, and third one will be this one. After solving this, we will get the first vector v1 corresponding to eigenvalue lambda 1 minus 1 as 1 0 0. v2 will be obtained corresponding to lambda 2 as minus 1 1 0, and v3 corresponding to lambda 3 will be obtained as 0 minus 1 1. These are column vectors, so you can see when they are written as row, there is a transpose indicated there. So we assemble v1, v2 and v3 as columns in V, and we get this V matrix. And of course for this V, we will have this as the V inverse. So this is the transformation matrix to diagonalize the given system. And of course the matrices lambda, the diagonal matrix will be V inverse AV, which will be minus 1, minus 2, minus 3 on the diagonals, and rest all the elements 0, like this. This is the short representation for this. And the beta matrix, when the system has been diagonalized, will be the column 0, minus 1, 1. So this is what we obtain after diagonalization. Now we consider the next canonical form, which is the Jordan canonical form, and this is obtained when the system matrix A has repeated eigenvalues. Because in this case we will not get n eigenvectors because the number of eigenvalues are less, and the few of them are repeated. So previous method will not work for the diagonalization. Instead, now the system will be transformed into Jordan form. Here the system matrix will be J, input matrix will be beta, and J is a Jordan form matrix. We saw while converting the transfer function representation to state space representation that Jordan form matrix consists of eigenvalues along the diagonal and ones on the subdiagonal, remaining zeros. This we have seen earlier. So we want to transform through an appropriate transformation this system matrix A to this J, which will be in this form. The eigenvalues on the diagonal and ones on the super diagonal, remaining entries 0. So let us see how to obtain this transformation. So what we do is that as an assumption, the case here is that eigenvalues of A are not distinct, they are repeated. So lambda 1 has a multiplicity of nu 1, lambda 2 has a multiplicity of nu 2, and so on. Lambda k has multiplicity of nu k, and k is less than n. And of course, if you add this nu 1, nu 2, etc., you will get n. With this, what we do is we obtain the k eigenvectors corresponding to the k eigenvalues lambda 1, lambda 2, etc. up to lambda k by setting up and solving this equation. Please note, it is slightly different in the case of diagonalization because there was no repetition. We had set up A alpha equal to lambda alpha, and which is also written as A minus lambda I being an identity matrix, alpha equal to 0. So here, because eigenvalues are repeated, what we are doing is we have a similar equation, except that this repetition appears as a power here. And then we are going to solve for the eigenvector. Here the notation is Vi, nu I, that it will give nu I eigenvectors. So like Vi1, Vi2, Vi3, etc. up to Vi nu I. We are solving for the last one first by setting up A minus lambda I power nu I into Vi nu I equal to 0. So once we solve for this, then we obtain the remaining nu I minus 1 eigenvectors successively like this. This is a chain of eigenvectors obtained from this one. So what we do, this Vi1 comes from Vi2, Vi2 will come from Vi3, and so on. Vi nu I minus 1 will come, nu I minus 2 will come from Vi nu I minus 1, and Vi nu I minus 1 is coming from Vi nu I. And you can see each one is obtained by pre-multiplying the eigenvector with A minus lambda I. Now, of course, it happens only when this Vi nu I is carefully selected, then only we get all the eigenvectors in the chain. If somehow this chain doesn't get completed, then we have to redo by selecting a different Vi nu I which satisfies this equation. Of course, now when we have solved for all the eigenvectors, then the next job is to assemble these eigenvectors in the matrix V to set it up. So this nu one column vectors, eigenvectors obtained previously as was shown, are assembled to get first nu one columns. Similarly, for lambda 2, we will get nu 2 columns, and so on. For lambda k, we get the nu k columns, and because nu 1 plus nu 2 etc. will become n, so these vectors are exactly n in number, and they are each one of is of length n, so this V is n by n matrix. And once we obtained the transformation V, then it is simple that the Jordan form matrix will be V inverse AV, and the corresponding input matrix will be V inverse B. So we consider one example. The given system is like this: 0, 1, 2, 0, 0, 3, 0, 0, 2. This constitutes the A matrix, and this is the B matrix for the given system. And we have to convert it into the Jordan form. So what we see, it is easy to find the eigenvalues, which are in this case, this example I have selected such that it is very easy to see that the eigenvalues are 0 with the repetition of 2, multiplicity of 2, and 2 only one time, no multiplicity, no repetition. So to transform the system into Jordan form, we have to set up these two equations. Because multiplicity is 2, we have to set up A minus lambda 1 I square. These two as this index. And we will obtain the last vector in the chain, and previous vectors we will obtain by pre-multiplication with V12. So we set up this one and we set up this one, and of course this I denotes identity matrix, and A matrix is this, which is again repeated here. So when we set up this one, we get this is A minus lambda I square. Essentially it is equal to A because lambda 1 is 0. So A minus lambda 1 I is same as A square in this case, and we are going to solve for V12 by equating this to 0. And one possible solution for this is V12, one possible solution for this one is this, V12 is 110. This is A square evaluated. Now once we obtained V12, then we obtain V11 by pre-multiplying V12 by A minus lambda 1I, and we get 100 transpose or column 100 as V11. We got two of the eigenvectors, V11 and V12. We obtain the third one corresponding to lambda 2 equal to 2 by solving this equation, and thus we have this equation, and when we solve this we get V21 as the column 764. And so we assemble these three vectors V11, V12 and V21 to obtain this V, and it is the required transformation. So next slide, we obtain V inverse, which comes like this, you can verify, and V inverse AV will come like this, V inverse beta will come like this. Now please note, the one of the eigenvalues was repeated, so we get a Jordan block this is lambda 1, this is lambda 1, lambda 1 and 1 and a 0. This is appearing here, 2 by 2 matrix here, and the other one which was not repeated was occurring only one is here on 2. So along the diagonal we have lambda 1, lambda 1 and lambda 2, and on the super diagonal here we have 1, and of course this was not repeated, so we have 0. This is what we get. So this is the Jordan form matrix, and corresponding beta of course is coming like this. We move to the next one, and now we have to consider how to transform a given state equation into companion form. We have two situations when we have a single input, and of course the procedure, once we have understood the case of single input, it becomes easy to understand the procedure for transformation of a multi-input system to companion form. So we start x dot equal to ax plus bu. You please see that this b, capital B, which I have been writing, is written as a small b, meaning that we are going to deal with the single input case first. So this system has to be transformed into companion form. So what we do is we calculate the controllability matrix Q. This will be discussed in detail in one of the subsequent lectures. Essentially, this controllability matrix Q is the matrix B, the column vector B, the input matrix, then B pre-multiplied by A, AB, and so on till we get n columns up to an minus 1 p. And subject to the system being controllable, we will find that this Q matrix will be non-singular. In case of uncontrollable systems, this Q will be singular. However, we are dealing with a controllable case. When we discuss controllability, we will discuss the case of system not satisfying controllability, how to still transform it to companion form. So we set up this Q, and then we obtain Q inverse and select its last row as the vector mu. And then once mu is there, then we obtain the transformation matrix as inverse of this matrix, in which first row is mu, second row is mu a, and so on. The last row is mu a n minus 1, a power n minus 1. So this is n rows obtained once we obtained mu as the last row of the matrix Q. And if the system is controllable, this inversion will be possible. So we will get V as inverse of this matrix. Then we have to, of course, invert V, and we have to get V inverse AV. This will lead to the companion form system matrix AC, and V inverse B will lead to companion form input matrix BC. So in the companion form, as we discussed in one of the previous lectures, that the system matrix has very interesting appearance like this. The last row is the coefficients of characteristic equation taken in reverse order. A1 appears last and An appears first. Last row is same as the coefficients of the characteristic equation. This column up to this one is zero vector, and the remaining part is n minus 1 by n minus 1 identity matrix. This is the structure of companion form matrix. So by transformation, using the transformation matrix which we have obtained here, we will get this kind of representation. And of course BC will also come in this form, where the last entry will be A1 and the remaining entries will be zeros. So let us see with the help of an example, a second order system example, where the A matrix is like this, corresponding B matrix is like this, and we have to convert it into the companion. So we obtain Q matrix by assembling B as the first column and A times B, this multiplied by this, as the second column here. So this is B, this is AB. And for this we obtain this Q inverse. You can verify by doing your own hand calculations. Now this last row of Q inverse is chosen as the vector mu, the row vector mu, which is here. And once mu is there, then the next row vector is mu times A. So this is mu and this is mu times A. And they constitute the columns of this matrix, inverting which we get V, which comes like this. Now once we got the transformation matrix V, then rest is simple. To obtain the companion form system AC, we get V inverse A B, and BC V inverse B, and we get AC and BC matrices. Now you can see this row is that coefficients of the characteristic equation taken into reverse order. This part is 0 and this part is identity matrix. Now we come to the case of multi-input systems, and here we see it will look little cumbersome, but once we have seen the case of single input system, it is easy to comprehend this part. So we have now B matrix, which is at least two columns or few columns, because we have here multiple inputs. So each input has corresponding column in B. B1 is for U1, B2 is for U2, and Bm is for Um. So there are M inputs, there will be M columns in B. And of course we assume that none of the B columns is 0. At least one non-zero entry is there in each of the B1, B2, etc. So we proceed like this. Let us say that nu1 columns, this B1, AB1, etc. up to A nu1 minus 1 times B1, nu1 columns will be independent, or this is called as the controllability index of input 1. So for each input there is a controllability index, and that many columns will be independent. So the input 1, the column 1 in the B matrix, leads to B1, AB1, etc., A nu1 minus 1 B1. Similarly, the input 2 will lead to columns B2, A, B2, etc. up to A nu 2 minus 1 P2. So these are the independent columns coming from considering the each input column, in each column in B corresponding to the respective input. This column B1 is for input 1, this comes from input 2, and so on. This comes from the mth input. And so we get nu 1 plus nu 2 plus etc. nu m columns as assembled together as P matrix. This will be a rectangular matrix. This will have n rows and n by mn columns. Then the one n by mn columns. This will be a rectangular matrix. From that, we have to select n independent columns to constitute the B matrix. So we select all the columns coming from the first vector B1, first column vector B1 in B. We select till we get from B2, B2A, B2, etc. till we get independent columns on all its left side, this side. So B1, AB1, etc. up to this are independent. Now B2 will be independent of this, then only we will take B2. A, B2 will be independent of B2 and all preceding vectors, then we will consider B2 and so on. In this manner, from P, we will constitute Q, selecting the n independent columns starting from the left. So let us say we get sigma 1 columns from input 1, sigma 1 plus sigma 2 columns from input 2, and so on. In this manner, we proceed. And we select, after determining the Q inverse, its mu nth row. This mu1 is the nu 1th row. Mu1 is the nu 1th row of Q inverse. That is coming from the input 1. Then mu2 is after assembling this one, because we had nu 1 minus 1 up to that index, we got the independent vectors from input 1. So mu1, mu1a, etc. up to this. After that, we have mu2, which is the sigma 2th row of Q inverse, and so on in this manner. So we assemble first mu1 vectors, then mu2 vectors, and so on, and then we get the matrix V by inverting this in this manner. And rest is simple. The companion form system will be obtained by pre-multiplying A with V inverse, post-multiplying by V, and BC will be obtained by pre-multiplying V with V inverse. Let us consider an example. We have a system x dot equal to AX plus BU, where A is a diagonal matrix containing diagonal entries as 1, 2, 3, 4, and the two inputs, that column corresponding to first input is 1, 0, 1, 0, and the column corresponding to the second input is 0, 1, 0, 1. So A matrix is like 1, 2, 3, 4, zeros here, zeros here, and B matrix is 1, 0, 1, 0, and 0, 1, 0, 1, like this. We have to convert it into companion form. So what we notice, that if we find A square B1 and A cube B1, we will notice that both of these are dependent on B1 and AB. Similarly, when we find A square B2 and A cube B2, we find that they are dependent on B2 and AB2. Hence, P is only essentially B1 AB1 coming from input 1 and B2 AB2 coming from input 2. And the same P is taken as Q because this B2 is independent of B1 and AB1, and this AB2 is independent of B1, AB1 and B2. So each vector is independent of all the preceding vectors. This Q is selected as P itself, and Q inverse will be this. You can verify. So mu1 is selected as the second row of Q inverse. This will be selected as mu1. This into half. Half is here. So we will get this is mu1, and mu2 will be selected as fourth row. This one. Half into this one. So we have mu1 and mu2, and then we assemble the V matrix. This mu1 here and mu1a here. This is mu1a. This is mu2 and this is mu2a. We assemble to get this V. This is mu1, this is mu1a, this is mu2, this is mu2a. Inverse of this is the transformation matrix V. Of course, now what is required is to do this operation V inverse AV and V inverse B to obtain the companion form matrix AC and the corresponding input matrix BC, and thus we get this. If we do that computations, we get this as the AC matrix. Now we note a very interesting structure, because the two columns came from the first input and two columns came from the second input. We get interesting appearance. This is a companion form matrix, and this column is the corresponding input matrix. This is also a companion form matrix, and this is a corresponding column coming from. Now this was a case, this example was very nicely made so that each input has controllability index of 2, and so we get, by applying this method, transformation to companion form in which each of the transformed system is appearing as a single input system. The contribution of input 2 here is coming 0. And also these states, they do not depend on the remaining two states, they are zeros. Similarly, the second set of states, Z3 and Z4, are not dependent on Z1, Z2, they are dependent among themselves. Z3, Z4 are dependent on Z3 and Z4 and only on B2. So in case of this transformation to companion form, a system in which there is no over-designed inputs. Inputs are only as many as the required ones. We will get this kind of structures of AC and BC. However, if the system is over-designed, generally we take more inputs than the required. This is to accommodate some failures of the inputs. And in that case, AC and BC will not come in this very good form. This some entries here and here may not come all zeros, and similarly here we may get non-zero entries. So with that example, we complete this transformation to companion form for a multi-input system also. We summarize this lecture. We have learned with the help of examples how to transform a state space model into canonical forms like diagonal, Jordan and companion form. Of course, these canonical forms, as I told in the beginning of the video, that they are useful in solving the state equations, assessment of controllability and observability, and controller and observer designs. Thank you. We will meet again in another lecture.